Warning: do not copy. Our programs are covered by registered U.S. copyrights. They may not be duplicated or copied. Willful infringement constitutes a felony punishable by fine and imprisonment. Civil remedies include statutory damages of up to $50,000 per offense, plus plaintiff's attorney's fees.
Basic Math for Electronics. Part 3. Series Circuits and Ohm's Law. In the last part, you were introduced to Ohm's Law. You saw how this important formula can be rearranged to solve for any unknown. You were also introduced to the power equation. You saw how it could be combined with Ohm's Law using a helpful memory aid in the shape of a wheel.
In this part, you'll use Ohm's law to solve series circuit problems. You'll see how voltage rise and voltage drop compare. You'll be shown how Kirchhoff's voltage law works. Let's get started.
A series circuit is an arrangement of components that requires the current to flow through each component, one after another.
In a series circuit, there is a voltage rise and a voltage drop. Voltage rise is the source of electromotive force for the circuit. This could be a power supply, a battery, or a wall outlet. These provide voltage rise. Voltage rise is present in a circuit whether current is flowing or not.
Voltage drop, on the other hand, is anything that opposes current flow, such as a heating element, a resistor, or a light bulb. For example, this lamp, when lit, has a voltage drop across it. Voltage drop can be measured across a component in a circuit when current is flowing. An important fact to remember is that in a series circuit, the voltage rise equals the voltage drop. Let's take a closer look at the relationship between these two.
Look at this schematic. Notice the symbol for the 6-volt battery. It has a long line at one end representing the positive terminal and a short line at the other end for the negative terminal. These terminals give a voltage source its polarity. This schematic also includes a resistor, a switch, and 2 voltmeters. With the switch open, a voltage rise of 6 volts can be measured across the source, which in this example is the battery, and a voltage drop of 0 volts across the resistor. After closing the switch to permit current to flow, you can measure 6 volts across the source of the voltage rise and 6 volts across the load resistor, which is the voltage drop. Anything that will limit the current flow is referred to as a load.
Pay particular attention to the polarity of the voltage rise and the voltage drop. If you follow the path of current from the negative terminal of the battery to the resistor, you see that that side of the resistor is negative. This will always be true. The end of the load nearest the negative terminal of the power supply will be negative, and the end closest to the positive power supply terminal will be positive. Moving around the circuit from the positive terminal of the voltage source, notice that you have plus 6 volts and then minus 6 volts at the resistor. The sum of the voltages around the closed loop is equal to 0. In other words, the voltage rise is used up on the load and becomes a voltage drop.
When you add additional resistors labeled R2 and R3 to the circuit, the sum of the resistance values will always equal the total resistance. This can be written as the formula RT equals R1 plus R2 plus R3. The 3 periods after R3 mean that if there are more resistors, then proceed by adding their values as well.
Because there is only one path in a series circuit, there is only one current flow. This current is the same in all parts of a series circuit. Since the current is the same in all parts of a series circuit, it must flow through each resistor. The total current, IT, can be calculated using Ohm's law. But don't be confused. In this part, V will be used instead of the letter E, which you saw in the previous parts. Remember, E and V are interchangeable. The supply voltage, V, is divided by the total resistance, RT.
Using this series circuit diagram, let's solve some problems. V equals 30 volts. R1 equals 5 ohms. R2 equals 10 ohms. R3 equals 15 ohms. Remember, you can solve for the total resistance by adding them all together. 5 plus 10 plus 15 equals a total of 30 ohms. Now, solve for the total current. Using Ohm's law, the voltage, 30 volts, is divided by the total resistance that you just calculated, 30 ohms. 30 volts divided by 30 ohms equals 1 amp.
Now let's solve for the voltage drop across each resistor. Once again, use Ohm's law. Multiply the total current, which is the same at every point in the circuit, by the value of each resistor. The voltage drop across R1 is equal to the total current, 1 amp, times R1, 5 ohms, which equals 5 volts. The voltage drop across R2 is solved by multiplying the total current times R2. 1 amp times 10 ohms equals 10 volts. Finally, the voltage drop across R3 equals the total current times R3. 1 amp times 15 ohms equals 15 volts. You can now find the supply voltage by calculating the sum of the voltage drops. Remember, in a series circuit, the voltage rise equals the voltage drop. This is a handy way to check your values. 5 volts plus 10 volts plus 15 volts equals 30 volts. This example illustrates an important law in electronics known as Kirchhoff's voltage law. This law states that the sum of the voltage drops across the branches of any closed path or loop is 0. Here's the formula for Kirchhoff's voltage law. Vt equals V1 plus V2 plus V3.
Let's look more closely at how this law works. Pick a point on the circuit and label it A. Now move clockwise around the circuit. You will first encounter the supply voltage, plus 30 volts. Next, you encounter the voltage drop across R1, minus 5 volts. As you continue moving around the circuit, you come to minus 10 volts across R2, and finally minus 15 volts across R3. According to Kirchhoff's law, 30 minus 5 minus 10 minus 15 equals 0.
Let's start from a different point. Moving clockwise from point B, there is a minus 5 volts across R1, minus 10 volts across R2, minus 15 volts across R3, and plus 30 volts for the supply voltage. Minus 5 minus 10 minus 15 plus 30 once again equals 0.
This time, start at point C and move counterclockwise around the loop. Be careful, the polarities will change. First, you'll have plus 10 volts across R2, plus 5 volts across R1, minus 30 volts across the supply, and plus 15 volts across R3. Once again, according to Kirchhoff's voltage law, plus 10 plus 5 minus 30 plus 15 equals 0.
Let's work through another problem, this time using circuit values that you'd be more likely to find in a real application. This new circuit has a supply voltage of 25 volts. R1 is 10 k ohms. R2 is 15 k ohms. R3 is 25 k ohms. Total resistance equals the sum of these. 10K plus 15K plus 25K equals 50K ohms. Use Ohm's law for finding the total current. I equals the electromotive force, 25 volts, divided by the total resistance, 50K ohms. Do you recognize the metric prefix? What is the rule for dividing units, such as volts, by kilo? Units divided by kilo yields milli. You need only to divide 25 by 50. Did you get 0.5 milliamps?
Let's find the voltage drop across each resistor. V1 equals R1 times the total current, or 10 kiloohms times 0.5 milliamps, which equals 5 volts. Notice how K and M cancel each other out when you multiply, because adding the exponents, -3 and 3, results in an exponent of 0. Any number raised to the 0 power is equal to 1. So 10 times 0.5 times 10 to the 0 power equals 5 volts. Add this value to the schematic. V2 equals R2 times IT, or 15 kiloohms times 0.5 milliamps, which equals 7.5 volts. As a helpful side note, notice that any time you multiply by 0.5, you're actually dividing by 2. Put the V2 value on the schematic. The voltage drop across R3 is calculated as R3 times IT, or 25 kiloohms times 0.5 milliamps. This equals 12.5 volts.
Now that you have calculated each separate voltage drop, you can check your answer by adding all 3 voltage drops to find out if they equal the supply voltage. 5 volts plus 7.5 volts plus 12.5 volts equals 25 volts. Using Kirchhoff's voltage law, you can move around the circuit to see that plus 25 minus 5 minus 7.5 minus 12.5 equals 0.
Now let's look at power in a series circuit. You already know from the previous program that power, P, equals current, I, times voltage, E. Don't forget that V is being used for E in this program. Go back to the earlier circuit with these values and calculate the total power by multiplying the total current, 1 amp, by the total voltage, 30 volts. This results in 30 watts. You can also calculate the power through each component by multiplying the voltage drop across the component times the current. P1 equals 1 amp times 5 volts, or 5 watts. P2 equals 1 amp times 10 volts, or 10 watts. P3 equals 1 amp times 15 volts, or 15 watts. The power through each component has been calculated.
Try one more example using all of the formulas that you have been presented with so far in this program. This time, the power supply voltage will be 80 volts. R1 is 3.3 k ohms. R2 is 4.7 k ohms. R3 is 12 k ohms. The total resistance is 20 k ohms. The total current for this circuit equals the power supply voltage, 80 volts, divided by the total resistance, 20 k ohms, which is 4 milliamps. With this information, you can solve for each individual voltage drop. The voltage drop across R1 equals 3.3 k ohms times 4 milliamps, or 13.2 volts. Add this number to the schematic. V2 equals 4.7 k ohms times 4 milliamps, or 18.8 volts. Keep track of this value by placing it on the circuit diagram. V3 equals 12 k ohms times 4 milliamps, or 48 volts. Don't forget that the sum of the voltage drops must be the same as the supply voltage in a series circuit.
Remember, the power for each component is found by multiplying each voltage drop times the current. But keep in mind that in some advanced circuits, you may not always have current to use without first performing many calculations. Referring to the equation wheel, you can see that there is another equation that can be used for finding power which does not require current. E squared divided by R. Let's use it. P1 equals 13.2 volts squared divided by 3.3 kiloohms, or 174.24 volts divided by 3.3 kiloohms. This equals 52.8 milliwatts. P2 equals 18.8 volts squared divided by 4.7 kiloohms. V2 squared equals 353.44. This divided by R2 yields 75.2 milliwatts. P3 equals 48 volts squared, or 2,304 volts divided by 12 kiloohms. This equals 192 milliwatts. Now you can calculate the total power. 320 milliwatts.
Now, using everything you've been shown so far, solve for the unknowns in a final series circuit. Once again, there will be 3 resistors and a voltage source. It's often helpful to chart values when solving problems. Let's try this method. Draw a chart with 4 rows and 4 columns. Label the rows R1, R2, R3, and R total, and the columns I, R, V, and P. The known values in this circuit include V1 equals 32 volts, P2 equals 96 watts, I3 equals 2 amps, and RT equals 48 ohms. Keep in mind that these values are being used for clarity in this example and would not be found in actual circuitry. Insert these values on the chart.
Because current is the same in all parts of a series circuit, you can fill in all of the current values on the chart with 2 amps.
From Ohm's law, you know that R equals E divided by I, so you can solve for R1 by dividing 32 volts by 2 amps to get 16 ohms. Don't forget that E and V are interchangeable.
You now have enough information to solve for power 1. Let's choose the simplest formula from the equation wheel. P equals I times E. 2 amps times 32 volts equals 64 watts.
Notice in row R2 you have current and power. Let's solve for voltage. Referring again to the equation wheel, in the electromotive force quadrant, find the formula that contains the 2 variables current and power. For R2 you have 96 watts divided by 2 amps equals 48 volts.
The quickest way to solve for R is to use Ohm's law to divide the voltage by the current. 48 volts divided by 2 amps equals 24 ohms.
For R3 you have I and no other value. How can you find another value? Notice that you're given the total resistance. Do you remember the RT formula? Since you have all of the values except R3, revise the equation by subtracting R1 and R2 from RT. 48 minus 16 minus 24 equals 8 ohms for R3.
Now you can solve for V3 using Ohm's law. 2 amps times 8 ohms equals 16 volts.
P3 is found easily now using the power equation. 2 amps times 16 volts equals 32 watts.
Now calculate the totals for the 2 remaining columns. The total supply voltage equals 96 volts, and the total power equals 192 watts.
Let's stop here and review.
Current is the same in all parts of a series circuit. Kirchhoff's voltage law states that the sum of the voltage drops in a series circuit is equal to the voltage source. Total resistance is the sum of the individual resistances. Total power is the sum of the power used in each resistor.
In the next program, you will solve for unknown variables in parallel circuits using Ohm's law and the power equation.